Alright class, here we go with our Kirchhoff laws analysis. This is going to be some interesting math, some fun algebra, and a whole bunch of new rules and just ways of doing things that are just standard in this field, but take some practice for sure. So this might take a little while for you guys to pick up, but with practice, I promise you, the more of these problems you try, the easier they'll become. And we're essentially following the same procedure for every example. So that's kind of a nice, easy starting point. We're always going to follow these three steps. So first, we're going to label all of our voltage sources, resistances, and currents. Sometimes they will be given. We'll be given the voltage of the cells, the resistance of our resistors. Sometimes we'll have to label them as our variables, which we're going to be solving for using our fancy algebra and our systems of equations. All right, so once we have everything labeled on our diagram, we're going to first apply the junction rule. So this is also known as Kirchhoff's first law. I'll just call it K1. So if you go back in the slide or in your notes, you'll see that Kirchhoff's rule says that all of the current going into a node needs to be equal to all of the current leaving the node. All right, so what comes in, we usually call positive. What comes out, we call negative, and they need to be equal to each other. And once we've done this, created our equations using the junction rules, then we're ready to apply Kirchhoff's second rule, which is our loops. So Kirchhoff's first law is our junction, and that is using our current. And his second rule or second law is the loop, and that involves our voltage, our change in potential difference. So we're going to create our equations with these variables and these known values in them, and we're going to get somewhere between 3 and I think 5 for this course will be the most that we'll have to create. 3 to 5 equations, and then we're going to solve these equations either by substitution, which is the easier and my preferred way, or by linear manipulation. So this is getting into linear algebra. It can be hard to pick up on. It's kind of a skill in and of itself, and unless you've done it in one of your math classes, it's going to be a little bit trickier. But we'll get going with this. I'll actually work through these with you one by one because they can be a little bit confusing. So this first example, we have our voltage sources, our cells. We have one that's 10 volts on the left side, and we have one that's 20 volts on the right side. I'm gonna get this drawn up on a whiteboard for us so that we can solve it together. Then we're going to have, they've already labeled the current and the resistance for us, which is nice and easy. They're saving us lots of work. They've even labeled our junctions. You can see A is one junction at the top, in the middle, and B is the junction on the bottom. What a junction really is, any place where 3 or more wires are meeting. So in this case, both of our junctions have 3 wires running into them. And finally, we have our loops. That's inside. We have 1 going clockwise on the left and 2 going counterclockwise on the right. And they even give us the resistance of all three of our resistors: 10 ohm, 20 ohm, and 40 ohm. So all we really need to think about on this one is our currents. That's the only thing we're solving for. That won't always be the case. Sometimes you'll have to solve for either voltage or resistance, but in this case, current is what we're looking for. I1, I2, and I3. I3 is assumed to be going down. So you're always, with a problem like this, just going to have to guess the direction of your current, and you'll see that if you guess incorrect, you'll get a negative answer, and you can just switch that around. So let's go through these steps together. So first of all, we are going to apply the junction rule at node A. So that's our first Kirchhoff's law. It's our junction. So at A, we have current 1 coming in and current 2. I2 is going to be this whole stretch. I2, I2. So we could even draw it there. A little bit of a redundancy, but similar. We would have I1 here. Because the current is going to be constant in the wire, even if we have a voltage change, right? The only time our current is changing is when we're splitting it at a junction. So current 1 and current 2 are coming in, and current 3 is leaving. So there's two different ways we could write that. We could write, since it's leaving, it being negative, and all of that is 0, right? Or we could write it like this, right? What comes in, I1 and I2, is equal to what comes out, I3. So either way you write out that first equation, they are identical. So don't worry about that. Now let's take a look at junction B. We have I3 coming in, and we have I1 and I2 both coming out, which you can see is identical to this. So we can actually ignore this one because it's the same. We need unique equations to solve for variables. If they're identical, might as well just ignore it and go on to your next step, which is Kirchhoff's second law. Our voltage across a loop needs to be 0. So for loop 1, we're going to follow the flow of conventional current, just because that is the conventional way of doing it in your electrical circuit analysis. So whenever you're looking at a cell, the bigger one is positive, the smaller one is negative, right? Our cathode and our anode. So our positive side is where our conventional flow, or a positive current, is going to be leaving, right? So as we've drawn it, right, as we've drawn our loop, we're having the positive come out, and it's the same direction as our loop. So whenever you have the cell and the loop matching up as expected, we're going to have an increase in voltage. If I were to have drawn this the other way, right, we're fighting against that conventional flow. Therefore, we're going to have a voltage drop across there. So if it matches, it's positive. So I would have 10 volts from this cell. If it were the other way, that would be a negative 10 volts. All right. So keeping track of the sign for this loop rule is one of the trickier parts of this setting up of equations. right? So if it is in the expected direction as shown by your cell, keep it positive, right? And very similarly, if your current is in the same direction as this loop across a resistor, right, it's going to do what would be expected, right, which is going to have a voltage drop across a resistor. So since the current is in the same direction as this loop, we have a voltage drop. So we're going to subtract our current times our resistance, because voltage is current times resistance. I don't know if you can see that there. All right, so we're keeping track of all of the voltages. They should add up to 0 by Kirchhoff's second law in each loop. So we're having a voltage drop there, so we're going to subtract 10 ohms times our unknown current 1. Okay, so staying in the same loop, we have I3 drawn down, so that's matching the direction of our loop. In this example, they're all matching, but in our next one, you'll see how that can change. So same direction, going across a resistor, we're expecting a drop. We have 40 ohms as our resistance, and our I3 is our current. And all of that should equal 0. All right, that's our first loop. Now looking at our second loop. Again, our loop is now going counterclockwise. If I were to have drawn it the other way, I would just have a negative supply, right? A voltage drop across my cell and a voltage increase across each resistor. But I've drawn it in a nicer way than that. So we have positive 20 volts because we're going in the same direction as we expect our conventional current to flow. Across this, right, we still have our current in the same direction as our loop, so it's going to be, as expected, a drop, 20 I2, and 40 I3, again in the same direction. All right, we have all of our equations. We got 3 equations, 3 unknowns. We are able to solve. All right, so in order to solve this, we're going to try using substitution. So whenever you're solving with substitution, you're going to eliminate a variable by substituting it in terms of your other 2 variables. So I'm going to substitute I3 for I1 and I2. I'm just going to take this equation, letter A, and I'm going to substitute all the I3s in my other equations for I1 plus I2. So I'm going to just do some adjusting here so I have room to write. Getting fancy. Okay, we don't really care about the circuit anymore. Now we're looking at the equations. Okay, so when I substitute I3 in to this first Kirchhoff loop equation, I end up with, so this is my modified first of Kirchhoff loop's equation. We get 10 volts minus 10 I1 minus 40, and then in brackets, we're getting, instead of I3, I1 plus I2. We're just substituting I3 for what we know it is equal to. And that will equal 0. And I can simplify this, right? Might as well do that now. I'm going to want to solve this for I2. So I'm going to bring I2 to that right-hand side. 10 volts minus 10I1 minus 40I1 minus 40I2 equals 0. I'll bring this over and combine our like terms here. So we can drop units at this point. It's weird for physics to drop units, but it just works nicely with this. So I'm going to subtract 50I1 is equal to 40I2. Okay, so I have an equation for I2. I could divide that by 40 again, but let's work on our second equation here. So again, just rewriting it and substituting out our I3, 20 minus 20I2 minus, and I'll just skip this intermediate step and I'll go right to minus 40I1 minus 40I2 is equal to 0. Now I can combine like terms and bring, I'll bring I2 to the other side again. So when I combine that, it's negative 60, so I'll bring it over to the other side as a positive 60. 20 minus 40I1 is equal to 60I2. All right, now I can solve for I2 in either one of those. So from here, I2 is equal to 10 minus 50I1 over 40. And I can bring this I2 now with substitution again into this equation, and I'll have everything in terms of I1. Right? So I actually didn't even need to do this intermediate step here. It'll make it a little bit cleaner, I guess. We have 20 minus 40I1 equals 60 times, I'm going to break that up into two fractions, 10 over 40 or 1 over 4. And then plus 60 times negative 50I1 over 40. All right, now all I have is I1. I ran out of room. Let me bring it up above. Okay, so I'm going to bring this guy up here. And I'm going to combine my like terms. 60 divided by 4, 15. So this guy's equal to 15. And I'm going to bring it over to the other side. So I got 20 minus 15 from this term. And I'm going to bring this one over to my other side is equal to 40I1. And then I got 60 times negative 5 over 4. Which gives me 75I1, negative 75I1. And then we got to bring them all together. We got 5 is equal to negative 35I1. And I1 is equal to 1/7. Negative 1 over 7. 5 divided by negative 35 is negative 1 over 7. and as a decimal, 143 amps. Where did you go? Right, and we see that since we have a negative, that means that we just assumed the direction of I1 incorrectly. It should actually be going the other way. Yikes. Sorry about the messy video. This is a tougher lesson for sure. So we got our I1 as negative 0.143 amps. So in actuality, I1, this current in this branch, would be in that direction, right? And we can solve for I2 using this equation that we substituted right here. I2 is equal to 10 minus 50 I1 over 40. I2 is equal to 10 minus 50. And we'll keep I1 as a negative because that's how we drew it. Negative 0.143 all over 40. And this one should give us 0.429. Let me double check my calculator. Minus 50 times negative . Yes, 0.429 amps. And our I3 is equal to I2 minus I1 from our Kirchhoff's first law, our junction, right? I3 is equal to I1 plus I2. Sorry, add them together. So that would be 0.429 minus 0.143. Giving us 0.286 amps for I3. Which apparently they didn't even ask us for. But it is important to know, right? So that current down the middle is 0.286. All right, long examples. Let's try this next one. They've got it unlabeled in the PowerPoint. I'll do it nicer for you and actually label it. Hopefully you guys got lots of paper at home because these questions take up a ton of room, as you saw by my almost triple whiteboard first example. And you can just imagine once you start throwing in series and parallel circuits. Sorry, series is easy, but when we throw in parallel circuits, this just gets to be an extremely long task. I had a course on this in university, and for all of the midterms and finals, you ended up doing max 4 questions. Some of the questions took 45 minutes. Lots of work. Okay, so they kind of describe the current here. I'll draw it as they drew it. And I'll show you how you can actually solve this one with substitution as well. So they've done it using linear manipulation, which works just as well. but I'll show you the alternative to that, which is again substitution, just like we did in our last example. So we got 12 volts on our left, we got 4 ohm and 3 ohm in that first loop. We got no resistors up top. And again, we got ourselves kind of set up almost battling against each other, I like to think about it. We got the positive ends pointed in the same direction. Okay, so they're numbering currents from left to right. So our middle one now is I2 instead of I3. So I1 and I3, they're assuming are running up. And I2, they are assuming is running down. And for our loops, they are assuming that current will flowing clockwise and left and counterclockwise on the right, just like we did in our last one. So I'm going to break away from the PowerPoint and show this example just on my own, go my own way. So we'll follow the same convention as them. This is our first loop, this is our second loop. Our voltage, I guess I probably should have wrote that, 5 volts on this side. Again, big side is positive, little is negative. So as we've drawn it, we got first to do our junctions. Call that A and that B. Right? So for Kirchhoff's first law with our junction, we got one equation at A, which is I1 and I3 going in. So I1 plus I3 equals I2. And again, for B, we got I2 coming in, I1, and I3 coming out. So we have a redundant equation. I'm not even going to bother writing it this time. So here's our first equation. In turn, we can substitute I2, nice and easy from that one. Second, we got our loops and the voltage across those loops. So in loop 1, we have our cell in the same direction as our conventional current and this first loop going clockwise. So that's going to be a positive 12 volts. And actually for the other one, I'm going to do it the opposite way so that we can just get an idea of what that would look like. Maybe it'll screw up my math, but it shouldn't. So 12 volts from here, and then we're going to have a drop because we have our current in the same direction as the loop. So that will be minus 4 ohms times I2. I'm just going to drop the units all together on this example. And another drop of I1 and 3. That'll equal 0. I don't know why I spaced it out so much. I need to conserve my room a bit better. And our second loop. So now I've drawn it backwards, so we're going to see weird things happening. We've got negative 5 volts because we're going in the opposite direction of the conventional current. Negative 5 volts. And continuing along our loop, we have the current I3 flowing in the opposite direction. So this resistor, since it's opposite of our loop, is actually going to be a voltage increase. So that'll be plus 2 times I3. And again, we got a voltage increase across this 4 ohm. So opposite direction, we're going to add those together. So that will be 4i2. Okay, so again, we want to work with some substitution here. We'll substitute in I2 for both of those and see how our math works out. So I2 is equal to I1 plus I3. We're going to throw that into this first equation with substitution. Substitute for 1, we get 12 minus 4, and then substitute I2 for I1 plus I3, so it's going to be minus 4 I1 minus 4 I3. I'm skipping our intermediate step. I'm immediately multiplying by everything that's in the brackets there, and minus 3i1 is equal to 0. I'll combine like terms and let's say bring I1 to the right side. So 3 plus 4, negative 7i1, bring it to the other side. We get 12 minus 4i3 is equal to 7i1. Okay, so we can go one step farther and solve for I1, which is 12 minus 4i3 over 7. Okay, this is what we're going to use in our final step to solve for I2. You'll see in a second what I mean. So our second equation, we've got negative 5 plus 2i3 plus 4, and now I2, we're going to substitute I1 and 3. I1 plus 4i3 is equal to 0. I'm going to bring my 5 over as well as I1. Do I want to bring out I1? Yeah. So 2 plus 4, we got 6i3 on this side. We've got positive 5 and negative 4i1. Actually, if I'm solving for I1 again, I'm going to keep 5 over there. There's 100 different ways to get to the same answer here, so don't worry too much how you get to it. So here, I'm going to solve for I1 by dividing negative 4 from both sides. I1 is equal to, so negative and negative becomes positive, 5 over 4, and this positive 6 and the negative 4 will become a negative 3 over 2. 6 over 4 simplified to 3 over 2 I3. Alright, now I can substitute this in to this equation. Alright, those guys are equal. So I'm going to substitute again, substitute my I1. Alright, so I'm going to bring this I1 into this guy here. So we get 12 minus 4i3 over 7 equals 5 over 4 minus 3 over 2 I3. I can break these up into two fractions as well. 12 over 7 and negative 4 over 3. 4 over 7. Alright, now I want to solve for my I3. Hoping that I made no silly math errors working with this many fractions. Has a lot of room for error though. So this is a bigger number, I'm going to bring this over, subtract. So 12 over 7 minus 5 over 4. And I'm going to add this to this side. 4i3 over 7 minus 3 over 2i3. So this side becomes 12 over 7 minus 5 over 4. I don't feel like doing that mental math. Good thing we got calculators. We got 13 over 28. This is feeling a little wonky, but we'll go with it. (13 over 28) is equal to, then I'm going to subtract those guys, so 4 over 7 minus 3 over 2. We got negative 13 over 14 I3. So to solve for I3, I'm going to multiply by the reciprocal. So I kind of ran out of room. I'm going to finish this up where I got lots of room over here. (13 over 28) is equal to negative 13 over 14, 3. So I'm going to multiply both sides by the reciprocal, and the negative to get I3 is a positive, negative 14 over 13 on both sides. So some fancy things are falling into place now. We get our 13s canceling out. Negative 14 over 28 is just negative 0.5 is equal to I3. Yeah, that seems right. So what does this negative mean? It means that I assumed the direction of I3 incorrect. So I3 is actually headed down. I also want to solve for I1, bringing I3 into this equation. I1 is equal to 12 minus 4 times negative 0.5. I3 is negative 0.5 over 7. So 12 minus 4 times negative 0.5 over 7 gives us I1 of I have to actually calculate it. 12 plus 2. I don't actually have to calculate it. It's just 2. And it's positive. And then I3 is equal to I2 minus I1 from this equation. So I should be solving for I2. Did that mistake twice. I3 plus I1, we got positive 2 minus 0.5, we get 1.5 amps as our I2. 2.5 in the opposite direction and 1.5. Did we do it? Yeah, we did it. Substitution. Maybe it's not easier, but the alternative is to combine your equations. They even created a fourth and a fifth equation using these. So what essentially you're doing with these linear manipulations is trying to cancel a variable. So when they combined this and this is equation 1, this is equation 2. They're combining them, they're just writing them all out. and they're trying to get rid of the I2. So since there was 4 I2 here and a negative here, they're multiplying everything up top by 4, adding them together. So the bottom stayed as is, 12, and then we got 4 I1 plus 3, 7. I2 cancels, that was our goal of this combination, and 4 I3. Then we can also combine this first and this third. And in this one, we also are trying to get rid of I2, right? Always try to get rid of the same variable, whether you're using substitution or linear manipulation, so that we're left with only 2 instead of 3 variables. So did the same steps here, ended up with this equation with no I2 in it. Now you can combine these two to solve for I1, right, through linear manipulation. So we're going to, actually, they're getting rid of I3, yeah. So I3, the top one is multiplied by positive 3, so you're left with 12 I3. 12 is the lowest common factor of 4 and 6. And negative 2 and 6 becomes negative 12. Those will cancel out. All right. If you are good at linear algebra already, that makes this a little bit easier as well. But I'm assuming that is quite foreign to you, and I wouldn't recommend learning it just for this stuff, because this is only a very small piece of our IB physics. All right. Let's call that a day, and we'll finish up this unit next week. There's just some small things to do. We'll see if we get a lab up and running. But talk to you guys next week. See ya.